This is chapter 6, question 41. Says in example 6.7, section 6.3 in the book, it was calculated that with the air track turned off, the glider travels 8.6 centimeters before it stops instantaneously. How large would the coefficient of static friction have to be to keep the glider from springing back to the left? So I had to look in the book for the example. But to solve this, we're going to start just with force equals ma. And then we want the force of friction, or lowercase f, minus the force of this. Oh, so let me back up here. So force equals ma. This would be the mass of the glider. This would be the acceleration of the glider. And F is the net force on the glider. So this is for the glider. And we want it to not bounce back. We want the acceleration to be 0. So when our acceleration is 0, this just comes out to 0, which means force of friction equals force on the glider. Now we can take our force of friction and set that equal to our coefficient of friction times mg. I'm not sure what this Greek letter is, but I'm really bad at drawing it. Equals, and for F, we can substitute in our k, so the spring constant and the distance it's moved. So what we're trying to solve for is our friction coefficient. So we can just go ahead and solve for that. Friction coefficient equals kd divided by mg. Now I believe we have all of our values for that. We do. We have 20 newton meters times your point. Over 0.1 kilograms and 9.8. And when you run that through your calculator, you're going to come out with 1.76 is your coefficient of friction. I think it's a static friction. I didn't specify that. So your static friction is 1.76, or your coefficient. Part B to this, see where it is. It says if the coefficient of static friction between the glider and the track is 0.6, what is the maximum initial speed, v1, that the glider can be given and still remain at rest after it stops instantaneously? With the air track turned off, the coefficient of friction, U of k, so your kinetic friction is 0.47. So first we're going to need to calculate the distance which the spring was compressed. We can use this equation here, but now we just need to solve for d instead. So it would be coefficient of static friction times mg divided by k equals d. We have our values for this. 6 times 0.1 over k, which is 20. And that comes out to our distance of 0.0294. So that's our distance. And let me erase some space for me to work. Next, we're going to use our work energy theorem. Work equals delta K, change in kinetic energy. For work, however, we're going to break it up into the work of the spring plus the work of friction. equals 1/2 mv2 squared minus 1/2 v1 squared. Our velocity 2 is going to be 0, so that will cancel out to 0. And then we can substitute the work of the spring to negative 1/2 kd squared. Plus the work of friction, which is already U of k mgd, or not U of k, I don't know what this letter is, but that's kinetic. Quite the equation we have here. So now we need to plug in all of our values. So you have negative 1/2 times k, which is 20 Newton meters, times d squared, which is our 0.0294 squared, plus your coefficient of friction, which was from our earlier equation, I believe. Yeah. Well, so it's the coefficient of kinetic friction, and this is actually negative for this. So this is 0.47 times our mass of 0.1 times gravity. And then again, our distance. So we're going to plug all these into our calculator, and then we have to multiply by -2 and divide by our mass of 0.1, and then take the square root of all of it. Let me run that through my calculator, and it comes out to be 0.67 meters per second. That is the answer to question B and A of 6.41.